Hello, ladies and gentlemen. My name is Malte from Krshiwoblozki. I work for Fraunhofer IZM in Berlin, Germany, and I'm leading the group System on Flex. And today I will talk about electronic textiles technologies. Here I prepared a little overview for you. I will first introduce the group System on Flex and what we are doing. Afterwards I will talk about electronics textiles in general. So I will tell you what we understand of electronic textiles. And then I will give you briefly 3 example projects that we have performed in the past. And then I come to my main part, which basically is covering the building blocks for electronic textiles and the technologies to realize these. So, first, coming to our group System on Flex, we are dealing with, or we are developing and researching and working on flexible electronics in general, on stretchable electronics, on conformable electronics, and on textile integrated electronics. In the field of flexible electronics, we usually work on advanced integration processes, flip chip technologies, ultra fine pitch flexes, chip embedding into flexes, and mostly the drive comes from the medical field, so we work on implants, on advanced medical devices and so on. In the field of stretchable electronics, we are working mostly on different substrate technologies, for example substituting polyamide with polyurethane and other derivatives, and more focusing on the substrate materials and on the assembly of these substrate materials. Conformable electronics is, in our view, something that where we also work with thermoplastic substrates. So we use conventional equipment to manufacture these, creating the tracks, assembling components, and but subsequently we use thermoforming or high pressure thermoforming to shape these electronics into a 3-dimensional form. But today I will focus on textile integrated electronics. What are electronic textiles? Electronic textiles, I consider it as an enabling technology that basically utilizes the benefits of the electronic worlds. That means power transfer, measuring, calculations, etc., with the world of the textiles, which means that we can basically use them as clothes. And this is also the first category I would like to point out. Textile is in the form of clothes, keeps us warm, protects us from the environment, also allows us to express ourselves in different styles. But if you introduce electronics into these kind of materials like clothes, you can do biomonitoring, biophysical monitoring. You can, for example, measure your heart rate, your muscle activity, your breathing rate. You can measure the movement of your body and so on. And therefore these textiles have to be breathable, they have to be very comfortable, very soft, very flexible to adapt to the shape of the human body. Another category of electronic textiles are, I call it textile equipment. For example, these can be backpacks or vests like displayed here, and or any other protective clothing in general. And these kind of textiles, they're manufactured with different technologies, so with different textile technologies, and they also use different materials. So they're also much more robust than clothes or underwear, for example. The third category I would like to point out are technical textiles. These again are completely different. They are mostly used in buildings, in automotive interior, and in any other big, large applications. And this is also what they are manufactured also in very large form factors. And this is completely different than, for example, conventional electronics manufacturing, which is usually in smaller form factors. And also, again, they are different with different materials and they have to fulfill different properties. And all these E-TEXTILES have in common that in the end you have to integrate somehow electrical conductors into these materials and attach and contact electronic components like microcontrollers, sensors, etc. to make them function. And because of these different properties, it's always a challenge to build them in a way that they fulfill product requirements and are functional over the whole product lifecycle. Okay, now I would like to talk a bit about some example projects that we have performed in the past. I will start with an EMG measurement project. This was part of the EU project Reframe, where we worked with the artist Jessica Smash to develop a user-centric EMG measurement piece of clothes. We utilized therefore our textile circuit board technology and did performed a lot of tests and research, and then we end up with the final demonstrator, which was basically a kind of clothing for the shoulder environment that incorporates different electronic electrodes to measure the muscle activity in the shoulder. This is on the inside, and on the outside we were able to put a little click connection to integrate the readout electronics. Another project, and it was for the demonstrator, the largest demonstrator that we ever realized, was the manufacturing or the development of a sensor sail for a company that develops sails. So they wanted to have real live measurements of airflow, of air pressure, of movement, of temperatures, to use these data for the simulation of their new sails, for the development of new sails. And we did this by integrating a kind of sensor network based on a textile ribbon that can be easily integrated into common test sails. And onto these textile ribbons, we integrated a lot of different sensors. We also developed the readout electronic box for that, which then can be connected to the main network of the actual test sailing boat. Another application, another project that is still running is called THERATEX. And in THERATEX, we develop a therapeutic system to develop a therapy for hemiparesis patients. And here again we use textile ribbons where we can populate different sensor modules, and these ribbons are then integrated in a knitted piece of clothes. In parallel, we also developed with a partner together the integration of conductors directly into the knit, where we then can populate our sensor units onto. And in this project, we use a combination of inertial measurement units, which can basically measure acceleration, orientation, and magnetic fields, in combination with dielectric elastomer stretch sensors for certain areas of the body to get a full picture of the motion and of the posture of the patient. And then followed up by the medical people who will develop therapies with these systems. Okay. This was all for the example projects. Now I want to move over to the building blocks that you need to build up electronic textiles. First, of course, you need to have electronic conductors. For every electronic circuit, you need a conductive materials that connects the components. And in the textile world, you have a huge diversity of different materials to do that. I will talk about this more in detail a little bit later. And then you need technologies to basically create electronic circuitry from these materials in combination with non-conductive materials, of course. And if you have these electronic circuits, the follow-up step would be to connect or use assembly components onto these to basically build the overall system. For the E-textile field particularly, it is important to follow maybe a different systems design approach, because in the textile circuit manufacturing, you don't have this huge freedom of designs that you, for example, have in the PCB world, where you can have, 10 to 16 different layers of electronic conductors and with vias and ultra fine pitch tracks and traces. All these you don't have in the textile world. So that's why you usually have to follow up, or have to realize it with some smart communication bus systems integrated into these textiles, and therefore the modules or the sensor units needs to be smart, or at least able to communicate via such a sensor bus system. Another thing, especially for E-textiles, is because they are so diverse, because the loads during the product's lifetime is so diverse, you need to do a lot of testing and also subsequently analytics of the failure modes to get better, to really find the weak spots and to engineer these weak spots in a way that they fulfill the product properties. Okay, so for us, we see it in a way that there are usually two ways to generate electronic textiles. The first way is where you basically have a textile with already integrated conductors during textile manufacturing, and then you can add components to that, and then you end up with an E-TEXTILE. The other way, which is also very common, is that you have any kind of base textile and you basically laminate a fully working electronic system onto that. That can be usually made of thermoplastic foils, and that is can, for example, be lithographically structured copper on thermoplastic foils, but also all the printed electronics that is then later integrated into textiles is basically going this way. Today I would like to focus a bit more about the first way, so where you also use textile integrated conductors. And therefore I would like to give a little overview about conductors in the textile field. And we usually put this into two categories. So on the one hand you have conductors that have a real textile character. So these are mostly polymer-based fibers or filaments that have a thin metal coating. The most common one is of course silver, but there are also more advanced derivatives for example with an aramid core and copper nickel gold finishing or copper silver finishing. And there are also super thin steel filaments. All these characters have in common that they can be used for any kind of textile manufacturing process, for example for knitting, for weaving, for direct embroidery, etc. The disadvantage is a little bit that the electrical properties not always fit the requirements from the electrical system. On the other hand, you have conventional, let's say, Litz wires, basically a bunch of copper filaments in a bundle, or you have so-called hybrid wires. You usually work with a non-conductive and textile-based core, and where the copper filaments are wrapped around. These core can be very stable and very, let's say, rough. For example, like an aramid core that can take all the force and keeps the force away from the copper filaments. On the other hand, it can also be an elastic core to create an elastic stretchable textile conductor. And the things on the right side, they can also be insulated. So the advantage of these is that they easily fulfill the electrical properties, but they lack a bit the textile character. So you always usually have a kind of trade-off, and depending on your application you have to choose the right material. And then another thing, last but not least, that we are currently also working on, but it is really, let's say, in its childhood, is the use of liquid metals, because they also have certain advantages, because they don't break. So the challenge is more the processing, how to structure them, and the weak spots are more the substrate materials around them. On the next slide, I would like to give you an overview about manufacturing processes for textile circuits, basically. To have it complete, I also included printing of conductors here. It's very common. You can use conductive base out of silver or carbon or combinations or even copper in some derivatives, print them onto foils, and then you can combine this with textile substrates. A more bare textile manufacturing process is knitting. In knitting, you create basically little loops out of the yarns and filaments, and therefore you create a stretchable and in the end very comfortable overall textile kind of network mesh. In this technologies you can also integrate conductive material, mostly conductive yarns, so the ones with the little metal plating. Another very diverse technology is embroidery, because there you can use any kind of textile fabric as a substrate, and you can embroider conductive yarns directly into the textile, so that they also build little loops, and that means that the conductive yarn also goes through the needle that is doing the embroidery. There you're a bit limited in the material choice, so you cannot use, for example, Litz wires or thicker wires with the insulation. But to do that, you need to do a specific derivative of embroidery, so you use tailored fiber placement, and with this technology, basically, material of choice is sewn onto any kind of textile substrate, and it offers a huge freedom of design. You can basically integrate any kind of circular material onto this substrate. Another very textile manufacturing process is weaving. So with weaving, you always have a warp and a weft yarn, and then you basically create a kind of interlock. Weaving is a technology that demands a lot of preparation and is has a certain, is quite complex, let's say. And in weaving you have also different versions. You have plain normal weave, you can weave ribbons, you have lino weaves that allows you also to integrate a conductor with a bigger freedom of design, and you have also jacquard weaving, which also allows a huge freedom of design. Other structuring technologies are for example from geodex, selective metal plating, where you can plate conductive materials directly on the textile fibers in a specific way. To complete this whole thing, I also included our TEXPCB technology, where we basically use any kind of fully conductive textile, restructure that via laser, embed this afterwards into an elastomer foil, which can then be laminated into any kind of textile substrate. And here with the frames, I outlined the technologies that we also have in-house here at Fraunhofer IZM. So that means printed electronics, knitting, embroidery, tailored fiber placement, and TEXPCB. So when you then have your textile circuit board, let's say, ready, then you need to think about integration of electrical components into these circuit boards. And that's what my following slides will cover. Interconnection technologies, an overview. The picture here below, what you can see is, actually it's very old, so I think 12 years ago, we tried to embed bare day LEDs into textile circuits, and there we basically laminated these two bare day LEDs in between two fully conductive fabrics, and this is a cross section of this. But let me talk about general challenges of integrating electronic components into electrical circuits. And therefore I want to basically compare the industries a little bit. In the electronics industry, you usually work with rigid and very geometrically stable materials, and the accuracy is in the micrometer scale. In the textile industry, that is a bit different. Most of the materials are very soft, limp, some of them are very elastic, and that means they are geometrically unstable. And also the accuracy is completely different. If you're lucky, you work in a lower millimeter scale. The next thing is considering temperatures. Most of the common assembly temperatures, for example, for lead-free soldering in the electronics industry, is quite high, easily above 200 degrees C, often also above 250 degrees C. This is very harsh for most of the textiles, because most of the textiles degrade above 200 degrees C or even below. Another thing is that you have in the electronics industry, this is basically the standard. You have highly automated assembly processes that are possible because of the aforementioned material properties. And for the textiles, this is not so easy to adapt, because textiles are hard to handle in these kind of environments. And now I would like to present you some solutions or some technologies that you can use to do interconnects. On the first thing, that's probably the most common one, or started in DIY but is also used in some products. These are snap fasteners or press buttons. You have them into mechanically interlocking versions, but also in magnetic interlocking versions. In the middle of the upper row, there is crimping and splicing. This is very commonly used in the automotive industry. I think most of the seat heating systems are interconnected like that. And then you also have the embroidery, not only as integration of conductors, but also for establishing the interconnect or the contact in the same way. This is at the moment also being industrialized. All these three have in common that you can establish electrical contact at room temperature, so-called force-fit interconnects. On the lower row, there are technologies where you need elevated process temperatures. On the lower left, there is of course conductive gluing, usually epoxy materials with silver flakes filling, but you also have thermoplastic versions nowadays. Then of course you can still solder with low temperature solder or even with normal solder, depending on the product, depending on the application. And then you have, mentioned there, adhesive bonding, and this is a process where I will also talk a bit more in detail in the next slides. Another thing is to use ultrasonic bonding. Okay, talking a bit about adhesive bonding for electronic textiles integration. What is it? It is basically an adaptation from the microelectronic packaging, specifically the flip chip process, where you have, in this case, an electronic module in the upper right, which is taken by the machine. This is this green thing with the so-called LED on it, and the 4 contact pads on the bottom, and in blue you can already see a pre-applied adhesive. On the bottom, this is the textile with integrated conductors. These conductors also have a little small insulation. And the process works as follows. You make an alignment, and then you apply heat and pressure. And then you have basically interconnected the module with the textile substrate. And the advantage is that you can do a mechanical and an electrical interconnection in one process step. You can also contact insulated wires, and as the contacts are on the bottom side, no peel forces or bending loads can act on these contacts. And similar to the flip chip assembly, a high number of contacts is possible in the same process step. And another advantage is also that it's compatible with a lot of different textile substrates like knitting, woven, embroidered, and TEXPCB substrates. And on the module side, you can of course use conventional PCBs, rigid PCBs, but you can also use this technology in a little bit in an adaptation for flexible or even stretchable PCBs. Okay, we basically developed this technology in-house. We started to do this on flip chip bonding machines, and to be sure that it is also good and reliable, we also did a lot of reliability investigations. For example, we did temperature cycling, so we built up specific modules that allows us to measure the contact resistance with the 4-point measurement during the whole reliability test. And then we started temperature cycling with plus 84 degrees C going down to minus 40 degrees C in very short and harsh cycles. During that test, a lot of thermomechanical tensions are introduced into the samples, and that can also act on the contact itself. But the tests were really successful, so we didn't have any failures. And that's why we wanted to see the limits of our technology. So we did subsequently testing from minus 55 to plus 125. This is the green curve. And then finally we got failures at temperature cycling tests from minus 60 to plus 150 degrees C. But to be honest, this temperature range is out of the scope of many or most of the applications for electronic textiles. What we also did is humidity test. We put the samples in a chamber at 85 degrees C and 85% relative humidity for 1000 hours, and we measured here also again the contact resistance subsequently. We also did washing tests of different test samples over the years, and I can say that mostly the contacts survived very good. During washing, you have other failure modes that are mainly happen in the areas where you have conductors. So the conductors are breaking usually. Okay, but as we think the technology is very reliable and is a very good option for electronic textiles, we decided to go the first step into industrializing them, and that's why we built a big machine to be able to handle also bigger substrates than you can usually handle into flip chip, microelectronic flip chip bonding machines. So we built this machine, we call it E-TEXTILE bonder. And I will now introduce the machine a little bit. So in the first, you can process 1 by 1 meter, and you can use conventional frames that are already used in industrial embroidery machines. And these frames can have already the circuit inside, the textile circuit inside, and then you can just put this frame into the textile bonding machine. The next step is that this textile bonding machine picks up an electronic module with a bonding head and then puts the electronic substrates below the bonding head. And then a dual vision camera goes in between the bonding head where the module was picked up and the substrate itself. And then this camera looks at the contact pads of the electronic module and then at the contact pads in the textile circuit at the same time, and we can do we call it active alignment. Because textile substrates are not always accurately manufactured, so you need to look for every module itself. And then if you have aligned them properly, you can put the head down and start with the actual bonding process that I have already mentioned before. This was the general process of adhesive bonding. And the next slide I will talk about our efforts to drive this bonding towards an fully automatic process. And therefore I would like to indicate the whole bonding process again. So basically, if you want to assemble models with adhesive bonding, you need to first clamp in the textile, put it in the frame, put it in the machine. The next thing is the machine picks up an electronic module, and then you move the frame roughly to the position where you want to bond the electronic module. And then there comes the optimal position. That is the process where the camera moves in and you do the accurate alignment. And then if this is done, you do the bonding. All of these processes are at the moment done manually by an operator. And for the optimal positioning, what you are doing is you basically move the textile in X and Y direction, and we are able to rotate the module. So during optimal position and optimal translation of the textile and the rotation of the electronic module is found. And as mentioned before, this task is currently done visually by an operator and is therefore time consuming. If we are able to fully automate this process, we can save a lot of time, and this process finally gets interesting for the industry. And therefore we developed the so-called Bonder Vision system. The Bonder Vision system still supports manual workflow, which is very important for us in the research. We first start with the detection of the pads, so we wrote an algorithm for that, with machine learning also, and the second step is to detect the conductors. Then the third step is to get an optimal translation and rotation by finding pad-conductor correspondences and solving an optimization problem. So basically the machine calculates the optimal position. And then these positions are transferred to the machine, and the machine then automatically applies these and does the alignment automatically. And our vision is really that we can feed the machines with a certain number of modules, and afterwards feed it also with a textile, and then it is doing all by itself. And last but not least, I have put in just a screenshot of our actual software. And with that, I hope it was interesting for you. I would like to thank you for your attention. If you have any questions, ask them now, or I'll probably also will check the chat. Thank you.